So we are going to be looking at our last section in chapter 10 with single data, single samples. And this is 10.3, it's over hypothesis testing for the sample mean, which is quantitative data. So let's turn in your course packs to page 235. And you can see that this is also not printed correctly. So I'm going to suggest to get out your yellow sheets and let's just write down which one matches from our yellow sheets. And that would be your yellow sheet, page 268. So let's just put that here on our white sheet, page 268 in yellow packet. So let's go to the yellow packet here. And it's the t-test that we're going to be looking for in our calculator. And then in StatCrunch, we're going to be doing statistical tests, but we're not going to choose Z, we're going to choose t-test. Because remember, when we're trying to talk about estimating, we have to use the t curve instead of the normal curve when we're talking about means, because we don't know the true standard deviation of the population. So our requirements are from the CLT that we've studied before back in chapter 6 and 7. Random sample, sample independence, only if we're sampling without replacement, making sure our sample size is less than 5% of the population size. And our check for normality, if our sample is not bigger than or equal to 30, we have to check that there's no outliers using the normal probability plot. Again, the rest are going to be very similar to 10.2 as far as we have a left-tailed, two-tailed, or right-tailed. One difference is going to be the symbol. We're using mu instead of p because we're talking about quantitative data instead of qualitative data. Left-tailed is still a less than, right? Two-tailed is a not equal to, and right-tailed is a greater than. And then your mu0 is your sum value that you think is true about the population. Step 2 is the same. It's just our level of significance alpha. Our test statistic in step 3 is similar to a z-score, but remember we're using our standard error, and it's our observation from our sample mean subtracting the population mean. Our step 4 is going to be looking almost identical as well, and then step 5 will be identical, and still will step 6. So let's turn to page 236 to look at our first example here. So it says the average credit score in 2019 in the US was 703. A researcher for Capital One Bank believes the credit score for their customers is different than this value. Okay, they believe it's different. So let's underline that because that's going to tell us something. And back in 2019, we knew that this was the mean of the population. They gather the following credit scores from a random group of Capital One customers. There are 19.6 million Capital One customers. That's our 19.6 million is our population size. This sample data set is available on StatCrunch. So we could get that from StatCrunch, or we could go there and type it in. But let's look at our conditions. It says verify that the conditions to conduct a hypothesis test are met. So our first one is random, and they did tell us that they got a random sample from their Capital One customers. So there we go. The next one is independence. And we just need to make sure that our sample size here, they said there were, I think 30, 2, 4, 6, 8, 10, 12, 14, 16, 18, 28. So 28 is less than 5% of the 19.6 million. So let's just figure out what is 5% of 19.6 million is, so yep, 28 customers is definitely less than 980,000. So yes, that's true. And then our sample size is not bigger. Our sample size is equal to 28, which is less than 30. So we need the plot. So we use our normal plot here, and it looks linear. So it's good because it is linear. Okay. So B says, go ahead and conduct the hypothesis test at that 0.05 level of significance for the mu, showing all steps, graphs, formulas, and substitutions. So our first step is our hypothesis statement, and we are testing the mean, and they think the population was 703 back in 2019 was the credit score, national credit score for their Capital One customers. And now they think it is something different. They believe it's something different. So a not equal to 703. And then remember that step 2 is our alpha, and that level of significance is equal to 0.05. And then our test statistic T, which we said is equal to the sample mean minus the population mean over the standard error. So that would be the sample standard deviation divided by the square root of n. And so we have to put our data in to find all this, right? Let's just kind of get our graph and everything set up for the rest. So we're talking about not equal to, so our curve is going to look something like this. And then, of course, we're going to be comparing our p-value to our alpha, and we said our alpha is 0.05. And then once we know if we're going to reject, we'll go ahead and write up our statement here. So let's go ahead and go to StatCrunch and look at the data here. So here is our data in StatCrunch. I typed it all up. And we are going to go to stats, and then you're going to go down to T-stats, okay, one sample and with data. And we're going to tell it says our var1. We could have named our var1, but we're just going to say var1. And we're not going to group by anything. We're going to just leave it as its natural listing here. And our hypothesis test is mean is equal to, and we have to put in 703. And then it's a not equal to, which they already have. And so we can just go ahead and hit compute. And there is our test statistic. You can see all that right there. Our test statistic, our degrees of freedom is 27 because we had an n equal to 28. And then our p-value. And then we do want to write down our sample mean and standard error so that we can write that in our formula. So our sample mean is 634.61 minus 703. And then they already calculated our standard error. So the whole entire denominator is 21.29. We'll round that to. And then our p-value is 0.0034. So let's go ahead back to our course pack to make sure that we all have the same bits of information written down in our paper. And here we are. So there's our sample mean that they gave us, 634.61 minus our population mean. And then this is our standard error that they gave us. Our p-value is 0.0034, and it is less than 0.05, so we do reject H0. And remember, our p-value is kind of split up between these two spaces when it's a not equal to. And our T0 is the negative 3.21. And so this is the 3.21 negative, or T0 equal to 3.21. So if we're this many z-scores either way, we're considered unusual, but we're using the p-value method because they're interchangeable, and we do reject H0. So there is sufficient evidence to support. So there is sufficient evidence to support the claim that the average credit score for the US is actually there's sufficient evidence to support the claim that the average credit score for not the US but for the Capital One customers, right? Because that was our population, Capital One customers. We didn't say if it was greater than or less than, we just said it's different than the US. That's what we're saying when we say we do reject H0. Okay. Let's look at our second example that we have here. So page 237 here says, understand the difference between statistical and practical significance. So in Canada, the average age of a patient admitted to the intensive care unit, ICU, in 2000 was 64.5 years old. A hospital administrator believes the age of ICU patients has decreased since then. Ooh, she believes they decreased, okay. They gather a sample of 6,018 random ICU patients over the period of a few years and find the average age to be 64.28 years, with a standard deviation of 8.2 years. Are these results statistically significant at the 0.05 level of significance? Assume the conditions needed to conduct the test are met, so that's good. Are they significant? Well, let's just see. So we're going to put this into StatCrunch, right? So we want to see, let's just go to StatCrunch here. And we're going to just exit out of this. But let's just go to Stat and to t-test and one sample, but this time we have summary data. So the sample mean, they said, when they sampled their patients was 64.28, and their sample standard deviation was 8.2. And the sample size that they took was 6,018. And we thought that the mean was 64.5 years old. And they said it's decreased, so we're doing a less than test. So let's just see what we get here. So the p-value is 0.0187, and we're going to compare that to alpha of 0.05. So let's just go back to our share and make sure that we're all on the same page here. So we can see that, yes, our p-value is less than, so we are statistically significant. It says, are the results of great practical significance in this situation explained? So it says they've decreased from 64.5 to 64.28. Yes, I guess they have. But does it really matter? So practical significance is, does it change the care for them? Does it change how we're going to care for those patients? No, we're still going to give them the same care, right? So when a result has a small p-value, we say that it is statistically significant and reject the null hypothesis. But that does not always mean that the result is important. Okay? When a result is statistically significant, we can only conclude that the true value of the parameter differs from the value in H0 in the way we specified by H1. We cannot conclude that the difference is large enough to be important, or i.e. might not be a practically significant. So in this case, yes, it does look like the average age of their ICU patients is statistically significant to say it's less than 64.5 years because this was our data from our sample. However, it doesn't mean that it's practical. We're not going to give them any different care than we would if they were, a little bit older on average. So that's important to recognize. So we are moving on to chapter 11, and chapter 11 will be our last chapter for the semester. So we'll see you back for lesson 11.1.